Okay, do everyone hear me? Yes. Okay. Okay, so hello everyone. My name is Héloïse Leboucher. I'm a third-year PhD student. I'm working in Toulouse in the Quantum Chemistry and Physics Laboratory under the supervision of Ottimo and Matthias Rapaccioli. And today I'm going to talk to you about collision-induced dynamics of PAH-water clusters. So we already heard about pH several times this week, so I will only do a quick reminder. So pH stands for polycyclic aromatic hydrocarbon. They are a family of molecules constituted of carbon and hydrogen atoms, and that have structures like this, so with several aromatic cycles that are glued to each other. These molecules have several research interests, especially in environmental science and in astrochemistry. Indeed, we think that these molecules could explain the presence of strong aromatic ion bands that we observe in several regions of the interstellar medium. To be more precise, we think that the pH could condense on interstellar nanograins constituted of a core of carbon or silicon surrounded by an icy mantle. And you can see that among all the molecules that could condense on these ices, we have the pH and also water. And you can also see that with this surface acting as a catalyst, many physical and chemical processes could happen, leading to a large diversity of molecules in those kind of systems, including a large diversity of charge and protonation states. However, to study this kind of systems, we need accurate description of gas-grain interactions, and we are currently missing data for such data to feed the models. And so one of the goals of today's presentation is to show you some theoretical tools that could be used to gather such data. So our precise goal here today is to study this pH, so the PAH, and its interaction with a water molecule, several water molecules, in fact, and with an additional proton in the system. But then we have the question of the localization of this additional proton. It could be within the water cluster or on the PAH. And you can see that PAH presents 3 protonation sites. And so we may wonder about the influence of the proton localization on the properties of these clusters. To study these clusters, we are running low and high energy collisions to simulate the growth and the dissociation of these clusters, respectively. And so this study is done in the astrophysical context and is also motivated by experiments. I will say a bit more about them later. So for now, I'm going to present to you the methodology that we follow. And first, I'm going to present to you the method that we choose to compute the electronic structures. And so this method is called self-consistent charge density functional based time binding. So from now on, I will only say DFTB for short. It can be seen as an approximate DFT method, where DFT is probably the most used method in theoretical chemistry nowadays. It relies on the concept of electronic density. In the context of DFTB, this electronic density, written here as ρ, is written as a variation around a reference density. Then we do a Taylor expansion of the energy, and after a few more additional steps, we can write the DFTB energy like this. So I will not enter much into the mathematical details. What I want to emphasize instead is that all these terms of the energy that you see here are parameterized from reference calculations. And so once we have a set of parameters, we can use them to compute calculations that will be less expensive than DFT typically. And this allows us to make calculations on larger systems or with longer simulation times, or simply more calculations in a reasonable amount of time. And all of this methodology is implemented in a Daemon Nano package developed in LCPQ. Okay, so now I'm going to explain to you how we simulate those collisions. So they are, in fact, Born-Oppenheimer molecular dynamics. So we are calculating the temporal evolutions of our systems. So with DFTB to compute the electronic energy. So here on this picture, you have the example of a collision between a water molecule here and a protonated PAH water system. At the beginning of a simulation, these two systems are separated by a distance a, which is fixed by the user. But the two other coordinates of the water molecules are selected randomly between 0 and a maximum b, also called the impact parameter. and rotations are also applied randomly on our systems. This means that at the beginning of the simulations, our initial conditions are randomly determined. And so one of our goals when we are running collision simulations is to run a lot of them to have a good sampling of the initial conditions. Okay, so I will go on to the first part of the results, so the low energy collisions. We are using them to simulate the successive growth of the water cluster until 4 water molecules on the protonated pyrene. So here are the parameters for the simulations. So we have low energy, 50 milli-electron volt, quite short simulation, 9 picoseconds. And so here, this line here, more than 1,000 starting geometries correspond to the sampling of the initial conditions that I just talked about. As for the procedure in itself, so at first we have a collision between a water molecule and a protonated pyrene, as illustrated here. At the end of the simulation, we identify the largest fragment that we have. And then this fragment becomes the new starting point for the next collision with another water molecule. And we repeat this process 4 times to have, at the end, clusters containing up to 4 water molecules. Okay, so now I'll present to you the results. So as I said in the introduction, pyrene presents 3 non-equivalent protonation sites that are written here. So first we have the C1 site, which simply leads to the progressive growth of the water cluster and nothing more, no other specific behaviors. For the C2 site, apart from the progressive growth of the water cluster also, we observe the proton transfer from the pyrene to the water cluster. For this site, we run additional steps until the step number 10 to see the evolution of the percentage of proton transfer along the step number. So this is represented here. So we can see that the proton transfer start to happen at the step number 3. So when we start having clusters containing 3 water molecules, and then this percentage increases until what looks like an asymptotic limit. And for the C4 site, we observe yet another behavior, which is this time the oxidation of the pyrene by one of the water molecules. So we see that the protonation site has a clear influence on the typical structures that we will obtain for our mixed clusters. And now we can wonder what would happen if we had a longer simulation time than 9 picoseconds. So we try other simulations with 0.25 nanoseconds, so with the exact same procedure as before. With that, we observe that the so-called special behaviors, so proton transfer and pyrene oxidations, are slightly facilitated. But what we mainly wanted to observe were the structures, because with a longer simulation time, we can expect a convergence of the geometries. And to study the structures that we obtained, we simply count how many water molecules were close to each other at the end of each simulation. And from that, we observe results that differ from the structures obtained from a more usual exploration method, because with those more usual methods, we tend to obtain the lowest energy isomers in which the water cluster adopt a cyclic arrangement, so typically triangle or square shape. But with the collision simulations, we more rarely found this structure, and instead, we mainly retrieve structures in which the water cluster is partially or totally separated. And then we highlight a dependence on the graph conditions for the structures, typical structures that we will obtain. And this is an important information for both the structures obtained in specific astrophysical conditions and also for the structures that we have in the experiments. Okay, so now that we have spent time building our clusters, I suggest to you that we break them. So I will go on to the high energy collision part. So here high energy means 7.5 electron volt. We are going back to quite short simulation, 3 picoseconds. And here the collisions are done by an argon atom. So this is the one in yellow here on the right. So upon collision with this argon atom, we will have a dissociation of our clusters. And since we are dealing with protonated systems, one of the fragments that we will obtain will be charged. And so, by running many simulations, we can reproduce a theoretical spectra that could be compared to the experiments. And more generally, theory can be used to complement the experimental data. Okay, Okay, so I will present to you the results. So we begin with a simple case of with one water molecule. We tried two different initial geometries for our cluster, and they correspond to two protonation sites on the pyrene. So here are reported the theoretical mass spectra. So you have no number of simulations leading to a corresponding fragment according to the M/Z ratio. And so for both cases, we observe the same thing. So the scale is not the same at the bottom, but the peaks are indeed the same. So we have here the pyrite ion, and then the peak corresponding to the loss of the water molecule. And that's all for now. Now we are going to n equal 2. So here we tried different starting points. So we have a starting point in which the water was initially within the water cluster. And yeah, for the other, the same as before. And here we observe different behaviors depending on the initial proton localization. Here on the right, we still have the loss of the water molecules, and that's it. But here we observe different dissociation ways. We have here the loss of the water molecules, and here the loss of pyrene, followed by the loss of water molecule. So we can see that the proton localization has also an influence on the typical dissociation ways that we will observe upon dissociation. And so this is the same for the following stoichiometry. So I will go on more quickly. Equal 4 and n equal 5. Okay, so now the important thing to note is that none of these theoretical spectra perfectly reproduce the experimental ones. And so we suppose that we have to mix our theoretical spectra in certain proportions to retrieve the experimental ones. But that's not it. With the theoretical simulation, we can also produce graphs like this, which represent the evolution of the proportion of fragments along the simulation time. So this is a graph for, again, the simple case of n equal 1. And here we simply observe the progressive loss of the pyrite ion and the formation of the protonated pyrene fragment. So this is really the simplest case. But of course, we can do the same thing for the other, and typically n equal 4. And here on this graph, the important feature to notice is this bump here. And this bump means that at the beginning of the simulation, we have the formation of this fragment and then another fragmentation. And you can see that this bump happens for the fragment that corresponds to the loss of one water molecule. This means that we have a quick loss of one water molecule and then something else. In other words, in certain conditions, the fragmentations of our system is sequential, which is an information that is not accessible through experiments. Okay, so to conclude, our goal here was to study collision-induced dynamics of protonated pyrene water clusters with molecular dynamics simulations and the FTB to compute the electronic energy. We saw that both with the low and high energy collisions, that the dependence on the protonation site or localization was clearly established. We also see the importance of the collision process in itself, so typically for the structures that we obtain. As for the perspective, so as I explained in the methodology, the DFTB energy is parameterized, but of course, several sets of parameters exist. And through several tests, we noticed that other DFTB parameters could lead to slightly different behaviors during the growth of the clusters. And so this is a matter that we still have to investigate it more. And also, we also tried the collisions, the same type of collisions, but with the protonated dimer of pyrene. And so this is, in fact, an almost completed study, which was slightly more complicated because of the charge delocalization question. I can say more about that if you want after. Okay, so I would like to thank my two supervisors, Aude and Matthias, also our colleagues from other labs in Toulouse for the helpful discussions. So Christine, Aria, Sébastien, and Alexandre, who talked yesterday. We also like to thank CalMIP Computing Mesocenter for granting us hours of calculations, NanoXL Nanocosmos for the funding of my PhD, and of course, thank you all for your attention.